And we're recording.
Okay, we're very happy to have Gordan to visit us in person. Gordan got his PhD in Johns Hopkins before he did his postdoc at Accelerator and Fermilab, and he joined the faculty position, a joint position between Fermilab and U of Chicago. Today he's going to tell us about dark atoms and H-naught tension. Please take it away.
Sorry, there's a little technical difficulty here. Okay, great. Thank you for the kind introduction and thanks for the invitation. It's great to see people in person and to have nice conversations. And today I'll tell you a little bit about a paper recently with Nikita Blinov and Shirley Lee, where we're investigating a potentially promising approach to the Hubble tension with some advantages and drawbacks. And I'll get started by giving you just a brief little outline. So I'll say a few words to get us all on the same page about what we currently know about the status of Hubble measurements, both the direct and indirect ones. I'll talk a little bit about dark atoms and cosmological perturbations and how that's been brought into this conversation to think about theoretical models involving new physics that will preserve all the good things that we like about early universe cosmology, but give us a vehicle for increasing the Hubble rate. And then I'll talk a little bit about what the advantages and drawbacks of this are and where some of the challenges remain. So this is qualitatively very different from a lot of the approaches to addressing the Hubble tension, because one of the things that I'll just flag right off the bat is that unlike every other model for the Hubble tension, models in the framework that I'll be telling you about have the virtue, and they're the only ones to my knowledge that have the virtue of being perfectly compatible with the CMB itself. They come with other challenges and we'll step through them, and I'll leave a little of that for suspense. But we can get started by saying a little bit first about the Hubble tension just in general to get us all on the same page. Question?
So you'll tell us what medal you got in the H-naught Olympics?
You're like 3 slides away. Well, we were a little too late to be part of the medal count, but we were doping too much. But we'll get to the comparison with other models for sure. But I like this slide. This is from the Hubble Olympics paper. And this gives you an idea of exactly where the different measurements are. And this is all, of course, overwhelming and big to take in. But the big picture is that there's a long-standing, many sigma discrepancy between direct and indirect measurements, which we can map onto, late and early time measurements of H-naught. The early measurements are all indirect in the sense that we have a 6-parameter lambda CDM model that measures things about the early universe, either from the cosmic microwave background or from measurements of large-scale structure in the matter power spectrum. And this is then used to make a prediction for what H-naught should be at present-day redshifts. This assumes standard cosmology. And of course, there are these late-time measurements, which are in most cases quite direct. They're just asking what is the expansion rate today as inferred from observations of supernovae going off. And you can have discussions about whether there are systematics that apply to the comparison between these. But there's generally a trend, as you can see in this, that the early measurements all sort of cluster around smaller values of H-naught, which are in the high 60s in units of kilometers per second per megaparsec. And then the late time measurements, with some scatter and with some controversy regarding exactly how you would add in measurements involving the tip of the red giant branch, they generally tend to be clustered towards the higher end, closer to numbers like 73 and 74 in those same units. And if you take the comparison of error bars at face value, particularly those involving Planck and those with the Shoes collaboration, you can easily find yourself in a situation where this is some 7 sigma catastrophe. And so we'd like to be able to see if there's something that we can say about that. Of course, it might be an unknown systematic in at least one kind of measurement. It could be all of them, and there could be all kinds of problems. But I think it's fair to say that lots of smart people have looked into this and haven't found any obvious places where systematics could have affected this measurement. That's been going on for many years now, although still logically possible, as we know. And it might be evidence of new physics insofar as the mapping between the early time measurements and the present day value of H-naught requires a theoretical model. and perhaps the assumptions of the model that's currently being used are faulty for whatever reason, and call for new physics to help patch that discrepancy. So that's going to be the working premise for the rest of the talk. So of course, it might still be possible that one of these other issues is plaguing the comparison, but we're going to assume that it's new physics, and we're going to see how far we can get by throwing dark atoms at the problem.
Can you say a few more words about the gravity wave related measurement? What's the nature? What kind of direct measurement?
Good. So this is a direct measurement, but it requires things that we don't really have very high statistics for just yet. So this would be a linearly independent way of measuring H naught, and it involves mergers of black holes and some kind of visible counterpart. And so you use the visible stuff to give you an idea of exactly what the distance is, and then you can use the waveform to get the redshift, so you can put it on the Hubble diagram to give yourself a measurement of H naught. The drawback, of course, is that there aren't very many examples of this, which is why these error bars are enormous. But depending on just how lucky we are, within the next, say, decade or so, this will give us a very different answer for what H naught is. And hopefully that'll resolve it once and for all, if it is just a measurement issue. But we're not quite there yet.
Yeah, when you say it's independent from all the other late measurement from what? From theory assumption?
From super, so it's a late time measurement. So you are really just like getting data from the, redshift 0 universe, and you're doing that based on astrophysical cosmological measurements. You don't require lambda CDM to get that. That's the important thing, because for each such event, you get a data point that gives you a distance and a redshift, and that's all you need. That slope will give you Hubble, and you get enough of those, and you have that measurement.
Redshift you get directly there, or you get it from the other astronomical objects within close to planets and galaxies?
I think the latter. You can figure out where it's coming from, and then you can do business with that. Yeah, but you've now exhausted my knowledge of this topic. But yeah, so that's the thing that I'm going to be most excited about going forward, just because it'll give us a different window into this. Whereas, like, you could always argue whether tip of the red giant branch and the shoes approach or plagued by common systematics or whatever. So it'll be a direct measurement that's just like in a very different category of things. Okay. But for our purposes, it's worth thinking a little bit about how we make the measurement of H naught, or how we at least make the inference of H naught based on the cosmic microwave background. And there, the important quantity here is the sound horizon at the time of recombination at LSS, the last scattering surface of the CMB. And this is related to the sound speed and to the expansion history. And anytime the expansion history enters into a measurement, you have an H as part of the problem. And of course, H as a function of A can be written in terms of the present day value of H naught, which is where this comes from. And so if you measure the sound horizon for features in the CMB, you can work backwards to figure out what H naught is. But of course, that requires you to have a model for what H of A is, because it's sensitive to the integral of what's going on as these sound waves are propagating in the early universe. And so if you change Hubble to a noticeable degree around that time, or maybe even crazier, you change the sound speed, which you don't easily have a way to do, then you would change exactly how you make that mapping. So this is a highly model dependent quantity. When we look at exactly how different theoretical models have fared in trying to do that, changing H naught to do interesting things like maybe you're adding dark radiation, maybe you're adding primordial magnetic fields, you are adding early forms of dark energy that dissipate away just before matter radiation equality. People have thrown the kitchen sink at this. And as you can see, I can bring up the ruler here since we are measuring. These are Olympic medals. And the first thing that sort of stands out for me in this is that all the models are bad. Okay, every single one of them is terrible. And I'm sorry to the people who've worked on it, but I think that's a pretty fair statement that you're trying to resolve a 5 to 7 sigma tension. And the best that you're doing is having some high number of sigmas that feel maybe a little bit better than that. They all provide a pretty poor fit to the CMB data set. And the ones that do a comparatively better job, that are only in like the 2 sigma territory, involve some pretty wacky ingredients. You need to vary the electron mass and you need to add curvature. So at that point, you might ask yourself, do I really want to do that much violence to the universe to leave myself with only like a 2 sigma tension after I've done all of that? So at a certain point, you look at this and you say, there's so many different theoretical approaches to this. Most of them do a bad job. So is there a different way to maybe try to imagine how we would approach the Hubble tension here? Because there's strong motivation for thinking of things that would actually preserve a good fit to the CMB. And so that's where we're going with the rest of this talk. Yeah. The gold medal, I mean, at this point, it's graded on a curve. It's like not, it's like 8 karat gold or something. For as many sigmas as there are. But yeah, so this was, of course, put out before our paper and before papers in this general category of where we're headed now. So I'd like to say a little bit about dark atoms and why they might actually provide a different. I've missed you, Maxime. It's a very inspiring area of research. In order to talk about how you get to preserve the CMB perturbations in a new physics approach, it's worth talking a little bit about how we get the, say, CMB power spectrum or any of the other associated observables. So when we do cosmological perturbation theory, we define quantities like little delta, which is the density contrast for your favorite kind of species in the very early universe, and a velocity divergence, which is also species dependent. And then we write down Boltzmann equations from varying the Einstein equation, and we perturb the energy conservation equations and so on. And we end up with these fairly compact expressions, one for each kind of fluid that's in the universe at that time. And then the solutions to these equations, evaluated at the appropriate redshifts in cosmic history, can be mapped back on to the 2-point correlation function of temperature fluctuations. And then we get these nice theory predictions for what, say, the power spectrum is in temperature anisotropy as a function of multipole moment. And of course, lambda CDM does a remarkably good job with dark matter and dark energy and the appropriate ratios of matter and radiation and so on. So this is not something that's very easy to preserve. But there's an interesting observation made by Siracine, Ge, and Knox from last year, which is that there's an approximate symmetry of the system of equations that preserves the form of all the correlation functions that enter into the CMB. And it's a rescaling that, for the purposes of this slide, just think about it as a mathematical trick. There's some number f that you can use to rescale every dimensionful quantity, everything that has the dimensionality of a rate. So Hubble has the dimension of a rate. Any gravitational time scale is related to root g rho. That's another rate. And of course, there's the Thomson scattering rate. And if you rescale all of those by the same number, and then you appropriately rescale your initial conditions, this is going to preserve the form of all of your linear perturbations. Now, this trick breaks down if you consider nonlinear effects, but it is a statement about the stuff that primarily determines your correlation functions on CMB scales, which are well within the purview of the linear theory. So this is really interesting. It tells us that if you can find a way for any kind of new physics to mimic the behavior of this kind of mathematical transformation, then you have something that's automatically protected from all of the bad stuff that gives you a bad medal in the Olympics. So it's worth thinking about what kinds of modifications to the early universe you can make that would approximately map on to doing all of these things. The problem, though, is that right in your face, the first thing that you try to do, if you were to just say, okay, I'm going to rescale all of my energy densities of everything that we already know and love by some number f, just assume that everything is a little bit bigger than we thought it was, you run into the problem that we've already measured the CMB temperature, so we know the energy density and radiation, and we know what the ratio of radiation to matter is and all of that good stuff. So we don't have the freedom to do that within the physics of the standard model. That's written in stone and fixed by measurements that are long established. And of course, also the electron density and Thomson cross section are really well known. We don't have the freedom to perform that shift. And in fact, this is secretly one of the reasons that people play games involving changes to, say, fundamental parameters like the electron mass, so that you can give yourself a handle for some of these additional kinds of quantities. Okay, so we can't change anything noticeable about the standard model sector, but we can try to see how far we can get by adding a separate sector that kind of walks and talks like the standard model. So for the remainder of this talk, every time that you see a prime on any quantity, you should keep in the back of your mind that this is something that's pertaining to a hidden sector that has many of the same degrees of freedom as the one that we're already familiar with.
Does it saturate the dark matter, or?
In principle, we haven't said anything about that yet, but where we're going with this, no. The answer is we're always going to be in the regime of few percent of the total dark matter.
So, triple coincidence of dark matter, normal matter, and mirror matter.
So now you're getting to the point of our paper. And so, exactly. So there is this observation, and in their paper, oh crap, what did I do? Sorry about that. I got a weird pop-up. Okay, we're back. So at face value, it is a triple coincidence. And so the question is, can you actually figure out a way to make it not a coincidence? And that's what we tried to do in this paper. And we succeeded, but with caveats that we'll get to. So
this is the mirror copy.
That's right.
All copies are identical.
For the purposes of this paper, where they were considering this problem, they just assumed that you had these additional species to map onto those. So they were thinking about it from the perspective of people who do fits to the CMB, where those are the only things that you need. That would be the simplest way to do it. Yeah. Now you
really need the mirror stuff. No, I mean.
What you need is, and we'll get to this in a little bit, but what you mainly need is to ensure that it has some subdominant fraction of the total energy budget. You need to make sure that the ratios of matter and radiation are basically the same, or to within good approximation the same. And on top of that, you need to make sure that the timing of certain kinds of important events has a similar effect on cosmic perturbation. So for example, when we go through recombination, they need to do something that kind of walks and talks like recombination. So that's a quick.
I'm sorry to interrupt, but this kind of this object, they would be 100% of dark matter, or it would be just a portion of it?
Just a small portion of it. I think we'll see.
Why not 100%?
It'll only be about a few percent if I heard your question correctly.
Right. But I wonder why not the whole stuff. I mean, because if you introduce this new stuff, then you can save. You can say that all the dark matter is made out of it.
What you would need is for something else to be the dominant dark matter that doesn't have any role to play in that sector. That's right.
I see.
Yeah.
You have a separate microwave background though, right? You have the background in the gamma prime.
Exactly, you do.
So why does it have to be happening at the same time? Why do you care about when decoupling in the dark sector happens?
Because you would like to ensure that the timing of the growth of our perturbations is in step with the timing of what's happening in that other sector. So for example, our perturbation growth is sensitive to, say, when you transition from matter to radiation. It's sensitive to when you form hydrogen and things like that. These are discrete events that we can map. And so if in that other sector, you ensure that all of the same things happen at the same time, that automatically protects you from, at least even in the gravitational side, influencing how perturbations grow. Just from like the Poisson equation, where their perturbations are going to enter in as well.
And so this stuff would make up 20% of the dark matter.
Would make up about 6 or 7%, as we'll see.
Of omega, but not of the dark matter.
It would be about 6 or 7% of the dark matter. Well, so we'll get to that in a slide or two. But the mouse here is acting a little weird. I'm not moving it, but you can kind of see it doing a little Ouija board dance.
Yeah, I think it's probably the controller that they have.
Oh, is that right?
Yeah.
Oh, I didn't realize that I could control that. Oh, well, I'll try to keep it under control. But okay, so we have two sectors. The primed one is going to be the mirror sector, and we can think of it as a mirror sector for now, but I'll get into a more concrete model for how it would arise so that you wouldn't have to have this be a quintuple or sextuple coincidence. But at face value, that's kind of where we are with this. But the reason that this mimics the scaling symmetry is that now you're adding some additional component to all of these quantities that are now effectively getting rescaled by the fact that you've added the prime stuff. And so if it's a small contribution, then this is in brackets the kind of thing that would stand in for the number F that we've been talking about. You have to satisfy a few requirements. So as many people have already suggested, the hidden sector has to be colder. We don't want it to overclose the universe. We don't want it to cause a huge catastrophe in how much dark radiation there is. We obviously have handles on that. And if you do too much, it certainly wouldn't be a very good fit to the CMB to begin with. That's what we're after in the first place. We need to make sure, and this is important, that the density ratios of different fluids are the same in the two sectors. And we need to make sure that recombination happens at the same time. And maybe that's one of the more non-trivial requirements that we have to satisfy. It's maybe not so hard to have a different temperature and having the density ratios. Maybe you could sort of connect how different asymmetries arise in another sector, tie them back to ours. But really, why would recombination happen? I would say that's maybe one of the weirder things that has to be satisfied here. So dark atoms, though, it does seem, if you were to grant yourself these additional moving parts, what our friends showed is that you can have, for a fraction of the dark matter that happens to be in this sector. Now, this is a quantity that is the fraction of the dark matter today at late times. So at earlier times, if you go deep into the era of radiation domination, you're also counting the dark radiation from this other sector. But like in terms of what its present day fraction is, it's only about a few percent. And so what they showed is, and sorry, I don't know how to turn off the mouse, but
Maybe you don't use a point-based device. Just
yeah, okay, fair enough. I can just, yeah, good. I'll use my computer. Yeah, so you have about a few percent fraction in the present day dark matter that comes from the stuff in this hidden sector, presumed to have formed its own hydrogen and helium and whatever else it might have gone through. And the benefit of doing this is that you, for a fraction of the hidden sector's temperature that's also about 0.5 relative to our temperature, you can actually make H naught be larger than 70 in appropriate units and provide a really good fit to the CMB. So this is the first model that I'm aware of, or at least the framework within which one might attempt to build a model that has this property. So that's something that caught our attention. But we were also troubled, like Maxime, with all of these weird coincidences. Like, okay, great, this is an interesting point to make, but how would you ever build a model that does all of those things, right? At this point, it's more fine-tuned than I would ever consider plausible, at least the face value.
So if I understand, so if the temperature is, let's say 75%, or let's say 70%, so I can square it and make it half, and then square it again to make it a quarter. So you're saying there's 25% additional radiation.
Yeah, that's right.
And isn't that a lot for BBN?
It's at the boundary of BBN, but what we'll see is that BBN is a problem that this framework does have to deal with, and that's the most serious problem. So you're thinking along the right lines. So it's not a problem for CMB, of course, though, because this is a different model that we're working within. So this would correspond to a scenario where there's a preference for a larger and effective, but for BBN, it does make for some problems, which are more properly thought of in terms of YP, which is where we're going. And of course, the main problem here is that In getting that really good fit, what they needed to do, for reasons that we'll get to, is float the helium fraction. So the helium fraction is something that perhaps you shouldn't want to float, because we have a measurement of what the helium fraction is. There's some observed value in the present day universe, and that's represented here in the line that's labeled A21. And the ellipses that they find that also give the large value of H naught and a good fit to the CMB, if they allow themselves to float Y, put them at values that are uncomfortably low with respect to the observed value. And even beyond just the observed value, this is something that we can calculate from within the standard model. And the same number that we use as an input to those calculations agrees quite well with the observed value. And so this is not necessarily something that we want to play games with. And so we'll return to this issue, but that's the biggest problem in the framework. So why is there a helium problem? Well, one reason is that when we add this hidden sector, what we're doing is we're rescaling H naught effectively with the addition of these extra degrees of freedom in exactly the right proportions to look like we've merely rescaled everything in a suitable way. But one thing that it doesn't do is on the standard model side, it doesn't rescale the Thomson cross-section times the electron number density. And this is a quantity that's secretly related to the helium fraction. And so in order to make this kind of walk and talk like you did this rescaling anyway, you make YP a little smaller, and they allowed themselves the freedom to vary that in the fit and to do so within values that would make us uncomfortable with respect to the actual measured value. That's not something that I'm going to solve. And so since I've already admitted that, you can go back to doing other things. But what I will say,
Isn't it like having a helium fraction of 4.15 is like perhaps worse than the H naught problem to begin with?
it may be, yeah, it's bad.
Depends which error bar you use. I was thinking about that on the figure that he had, but
Yeah,
the figure had huge error bars
Mhm.
for the fit.
that's right.
So that was probably, but if you were taking the best fit
Yeah.
compared to the error in helium,
4.15,
then it would be probably much more than
Mhm.
7 sigma.
Mhm. That's absolutely right. And so what we'll do going forward is try to address Maxime's earlier questions about the multiple coincidence. The helium problem is going to remain to plague us in everything that I'll say going forward. And that's something that if one could figure out a way around this, would make this automatically the best possible model for the H naught tension. And I'll hope to convince you of at least that part for the remainder of the talk. But to review where we stand, what we really need is a colder hidden sector. We need equal density ratios of different components across the two sectors. And we need recombination to happen at exactly the same time in both sectors. And on top of that, we need a mechanism to generate a baryon asymmetry in both of these, because you're not going to automatically have the right asymmetry to give yourself all of these things to work out automatically. So it seems extremely fine-tuned. I think that's a fair assessment. But of course, in that original paper, it wasn't their motivation to build a model. So this is why we thought a little bit more about this.
Can you just say another word of why their helium is actually low? VBN should produce more helium in our helium because the expansion rate is higher.
That's right. I don't think they did a fit to BBN specifically. They just said, we're going to take the CMB data at face value, and we're going to allow YP to float.
Oh, the CMB, so the helium in the CMB.
That's right.
Oh.
So
It's actually even worse.
It's
Right?
fixing at this ME parameter, right? The
Right.
number of free electrons.
I see.
that's what it's doing, exactly.
So, but
And
it's actually worse, right? Because
it is, because then it goes down and then it goes up.
helium, but they actually make more helium
Mhm,
than the observations would allow,
mhm, mhm, mhm,
right? Because you have a higher expansion rate. So
mhm,
if they did a BBN calculation, their
mhm,
YP would actually be higher.
mhm, absolutely.
Yeah.
Mhm. Yep, YP is
And yet they're
a,
assuming it to be small. So they're not using the YP that they get from BBN.
That's
They
correct.
need to use it. Okay.
Yeah, so YP
In the wrong
is,
direction.
that's right.
Right.
Mhm. Yep, so YP is not taking to be the value that this framework would predict for BBN.
Right.
That's correct.
Okay.
Uh-huh. Yeah, you were just looking at the CMB and trying to preserve that agreement to the greatest extent possible.
I just look at BBN.
Yeah, that's fair. And this is the biggest drawback of this framework. So, but in addition to that, it's also an extremely fine-tuned proposal, because what you really need to make sure that recombination happens at the same time in both sectors is you want to preserve the thing that lives inside of the exponential that governs when recombination happens. That's the binding energy of hydrogen divided by the temperature. And of course, that depends on a number of different parameters that are physically related to totally different kinds of interactions and energy scales. So for example, alpha is set by the charge on an electron. This is QED physics, as we know. The electron mass is set by the Higgs sector and whatever its VEV is in Yukawa coupling. The proton mass, which enters into the reduced mass, is set by QCD confinement. And the initial temperature has to do with what was happening, you know, at very early times in principle, and that you could have a temperature ratio across the two sectors that's defined by whatever physics is driving inflation and reheating and so on. And so getting all of those things to preserve that same ratio across the two sectors seems like it would be kind of a miracle. You'd need an extraordinary coincidence to make sure that the ratio on one side is equal to the ratio on the other side. And so for the rest of this talk, I'll say some words about exactly what it would take to get all of those things to work out in a way that at least would avoid the fine-tuning problems, and then leave you with a catastrophe for helium and BBN. So we're not going to solve the helium problem here, but what we will do is provide a model that does what at least Knox and friends point out would be favorable for the CMB in resolving the Hubble tension. So we're first going to add a mirror sector with identical fields and couplings. Here I'm only writing the quantities that are relevant for actually performing the CMB analysis. But of course, we're going to allow ourselves the freedom to map the entire standard model into the primed sector, but we're going to populate them in a slightly different way to ensure that all the ratios and temperature differences work out in a way that we would like. And it's kind of like twin Higgs, but think about twin Higgs in a different way. So in twin Higgs, we normally think about there being, in mirror twin Higgs, a hidden sector that's related to ours with a Z2 symmetry, and that a hidden sector has a bigger Higgs VEV. Here, we're going to approach it from the opposite direction. We're going to demand that the hidden sector has a smaller Higgs VEV. We're not interested in the hierarchy problem, but we've copied it. And so there's going to be a smaller VEV in the prime sector, but since all the couplings are the same, and the couplings govern the evolution of in the strong sector, then lambda QCD is about the same value, up to some small logarithmic corrections that are sensitive to the value of the VEV ratio. And so to excellent approximation, the proton masses are going to be about the same. The electron mass is going to be a little bit smaller in the other sector. And what we can do to get the rest of the scenario to work out in a way that we would like is that we want the particle asymmetries to arise from an Affleck-Dine-like scenario for baryogenesis. And we'll review exactly how that works to get on the same page. So stepping back from the mainstream of this conversation, in a scenario of Affleck-Dine baryogenesis, you might have a scenario where you have some scalar, it's a complex scalar, and it carries a baryon number. Its particle is sort of like a squark, and you give it a consistent baryon number, although it could be any quantum number that you like. It could be a lepton number. It has some net B minus L, and you give it a potential. Now, the potential contains terms that both preserve B minus L, those that come with phi and phi star in tandem, and then it also contains small terms that involve an explicit B minus L breaking. That explicit B minus L breaking is what allows for a baryon asymmetry to be generated in the early universe. This is presumed to be a very small correction to the total potential, but it tends to be good enough to actually get you a very appreciable asymmetry. And then the final ingredient you need is some kind of interaction involving the Affleck-Dine scalar and the standard model. And it doesn't particularly matter what kind of interaction it is, as long as it enables an asymmetry that is built up in the scalar field to then be transmitted through a B minus L preserving process into standard model particles. To see how this works, we would first write the field in polar coordinates. Writing it in polar coordinates gives you terms which are B minus L preserving that only scale as the norm in the complex plane, the radial direction, but all the B minus L breaking stuff has some angular dependence. And since this is a 2D sort of problem, there's an analogy between how a field like this evolves over time and orbital mechanics. And so you can write down a baryon density from the B minus L current. It's related to the baryon density of the field itself, and a term which looks like angular momentum in the 2D plane. And you get an integrable equation of motion for the baryon density. So what's interesting about this is that if you had some field that started off at some position away from the origin in the complex plane, maybe because inflation kicked it around a little bit, you got some Hubble-sized steps and where this field ends up when it starts rolling after inflation ends, then its non-zero value undergoes a sort of winding process in the complex plane, because now if the potential were independent of the phase angle here, then this would be the statement that baryon number is conserved. You would just have something that when you integrated it with right-hand side set equal to 0 would tell you that the baryon density would just evolve in time with redshift. It would scale like a cubed. But because this is not zero, it tells you that if you started off at some non-zero field value initially, you would actually be able to wind yourself up into a non-zero baryon number as well. And so this is a dynamical way of generating a non-zero B. And so when you integrate this, you start off with some initial phi value, which is correlated with the scale of inflation, and then it undergoes something that's very familiar from orbital physics. It's just that the amplitude of this thing gets diminished over time because the universe is expanding. Oh,
So what sets the phi dot initially?
It doesn't have to have any initial value because it gets driven to positive values, because the right-hand side is a torque. And so you could, as long as it's displaced from the origin.
No, but does it matter for you which
It
way?
evolves it.
If
Oh,
it,
then you get baryons or anti-baryons.
exactly. Yeah, you can, the sign of the baryon number is your choice,
Yeah, so
but that's set by the sign of the coupling that lives in the potential.
Your lambda should be small though, right?
That's right. You would want it to be small because unlike every other baryogenesis mechanism, this one has the perverse problem of giving you too large of an asymmetry generically.
Well, but the lambda is what, I mean, if you're doing it in supersymmetry, then what you want is a flat direction. And so your lambda is breaking that flat direction. So you need, principle, you're looking in for directions when lambda is 0. And so then the field can just float out as far as it wants, and then when this happens. But yeah, you're right. Then you end up typically with order 1 baryon.
Yep. And this is the only mechanism to my knowledge which happens to have that feature. Everything else is like this struggle against washout or whatever other thing there is. And then, of course, once you've generated some non-zero asymmetry from the dynamics of this field, which is related to whatever is in the potential, then you would need to transfer that asymmetry to standard model particles while B is still non-zero. That's the name of the game. And we can use this to our advantage by now just imagining a 2-sector version of the same scenario. There's going to be one Affleck-Dine-like field. And what we're going to need to make sure that everything works out in a way that avoids any of those weird tunings is that we're going to have a hidden sector and a standard model sector that both get their asymmetry from the transfer of whatever was built up in that Affleck-Dine field. So in that sense, both sectors, even though they're imagined to be very distinct, are going to carry a common B minus L number associated with them. And what we're going to need are ways to think about the reheat temperature, the baryon asymmetry, and relate those back to the Higgs VEV in each sector. Because what we're going to want to do is ensure that the branching fractions that govern the energy transfer from the Affleck-Dine field into the two sectors, scale as the Higgs VEV to the fourth. That'll be the ingredient that makes it possible to engineer all of the things that we'd like. So this is now just a two-sector Affleck-Dine.
If I think of supersymmetry, it's the same score in each sector.
No.
One phi or you have two
There's
phi?
one phi. There's one phi, and it talks to both sectors. It's the only thing that connects the two sectors. Yeah. So there would the analogy with supersymmetry in this case would only be imperfect. Yeah.
So in this mechanism, you're assuming the universe is reheated because of the Affleck-Dine condensate decay, so that you can control both TRH and TRH prime to be proportional to
That's correct.
So that means you're overproducing the baryon asymmetry in our sector.
No, not necessarily, because the energy transfer is going to be set by the Higgs VEV, but the dynamic, the potential of the phi field determines how much of that energy density is biased towards particles over antiparticles. So yeah, so like I could reheat both sectors with no baryon asymmetry if I set the kappa parameter in that potential to 0. It would still be the case that you would.
CP pilot. You can, you have that.
Yeah.
You can adjust the CP.
Yeah, exactly. That's right. Okay. So the main thing that we're going to need is a situation in which we have the common Affleck-Dine field. We write down some operator with some suppression scale, and everything else is Z2 symmetric. The only difference here is that we're going to have our Higgs doublet and their Higgs doublet enter in squared in the operators, such that when we figure out exactly how much of the energy is transferred from one sector into another, it'll give us something that goes like the VEV ratio to the fourth. And the
Phi is charged under both standard model charges, both. It's got charges for both standard model and the hidden sector.
no, it's going to be a singlet under both, at least in terms of the gauge charges. But it's going to carry some B minus L number that we're allowed to write down. Yeah, it's important that it not be, because otherwise it'll thermalize the sectors. We're going to have a lot of trouble with that one. Yeah.
And it won't thermalize them otherwise?
Yeah, we'll get there. So we have to impose some requirements on what kinds of operators and suppression scales there are to avoid that problem. Because if it starts off being some condensate that then transfers energy to the two sectors, what you would like to demand is that once that transfers happen, that the two sectors don't reconstitute that phi, or that it doesn't mediate processes that'll connect them back. Yeah, very good. But the reason we're asking for this funny phi to the fourth, or sorry, v to the fourth scaling, is because the energy densities that the two sectors get are going to go like t to the fourth. And if those energy densities are in turn set by proportions of v to the fourth, then it means that the temperature is going to be linear in the VEVs of each sector. So they're going to be reheated asymmetrically by some order 1 amount. And that order 1 amount is going to set the number that you need to make sure that those two sectors have some like 0.7 temperature ratio, let's say, to connect back to the earlier part of the conversation. The important thing is that the temperature is linear in the VEV. Yeah.
So this X squared is just equal to the absolute value of the X squared.
H squared. Oh no, sorry. This is the Higgs doublet, not.
Higgs star, but I mean, is it just the absolute value of the Higgs star?
The HH star, you mean, probably?
HH star?
Yeah.
Okay.
So little v is 246 GeV, and then v prime is going to be what we would like it to be to make the story work the way that we like.
Okay, so my question is, if it is HH data, then that is just similar than all the things we tried.
That's right.
And then is there any reason to prohibit other operators like without this X star?
Not necessarily, no. Right. So you would have to make sure that what operators you do choose for this prevent you from spoiling the story. So for example, and we'll have a slide on this in just a little bit, but you do have to be very careful about choosing those operators so that you, because this is not something that, because, okay, so H squared, sorry, this is not H dagger H. Let me be careful about that. Sorry, maybe this was the source of the confusion, because this is not the norm of H squared. This is literally 2 powers of H and then something that carries standard model charge, right? That's really important, because if it weren't like that, okay, great. Yeah, otherwise, yeah, we could write down all kinds of operators that wouldn't have this behavior, and that would spoil the story. But we would like for it to be linear.
Sorry.
Yeah.
But you could still write down those other operators. That's a singlet.
You could in principle, well, no, but it's not a singlet because these are two doublets that
Yeah, I
are,
know, but I could write phi to anything that's the gauge singlet,
Mhm.
right? So I could do H dagger H. for example.
that's right. So we're gonna, yeah, we'll talk about what form of operator we'd like to have for that going forward. But for now, this is the general kind of thing that we're gonna need to see exactly where the scaling comes from.
Just a question about the Z2 symmetry.
Yeah.
The potential is not Z2 symmetric. Then.
The, sorry, no, the Higgs potential should be okay, because the Higgs potential is just gonna be H dagger H.
No, but you've got V prime and V. You've got two different.
It's
You've
not
got
a
two
real
different
difference.
symmetries.
Yeah, it's nothing wrong.
You've broken it. That's what I'm saying. Haven't you? Because your lambda and your mass of the Higgs potential is different to get V prime to be different.
That's right. That's right. So in the Higgs sector, it's like how you would get a different V in a twin Higgs model, for example. In the Higgs potential, you do need that to be different.
There's a Z2 breaking there, but that feeds into everything else that being loops.
That's
It's
right.
breaking. So
Mhm. That's right. But we don't need this to be better than, say, like, 10% in the two sectors. So if you're allowed to, because I mean, you can live within those ellipses, right? If you're literally at the best fit, then that's a dicey proposition. But we're not in that quite of a precision game here. But you're absolutely right. And so the virtue of connecting things, or setting the temperature to be linear in the Higgs VEV, which is the ingredient we want, then the binding energy is also going to be proportional to Higgs VEV. Because the binding energy is largely driven by the electron mass. So the electron mass scales linearly with the VEV as well. Alpha is going to be the same in the two sectors. So the binding energy for the standard model sector and the prime sector is just going to be set by the VEV. But of course, so is the temperature. So B over H is a constant, and it's the same constant for the two sides. And so that's what ensures that we're going to get the same redshift of recombination for the two sectors. Especially because lambda QCD is about the same thing in both. The baryon asymmetry that we get from this is now going to be set by whatever CP violating stuff there is, but that's going to cancel out in the ratio because we're going to assume that that's going to be the same in the both sectors. That would not be an example of the Z2 breakage in the potential of the phi, but the energy transfer does know about the VEV ratio. And because eta is also a quantity that depends on the entropy of the universe, the entropies of the individual sectors, you get something that is sensitive to the reheat temperatures that you get when the phi field disappears. And so up to this factor of G star ratios, which we could take to be 1 if this all happens at sufficiently high temperatures, or if it happens in between entropy dumps where you have the same number of degrees of freedom in both sectors, then it is just a function of the VEV ratio. So the asymmetries are a little bit different. But by doing this, you do ensure that the fluids have the same ratios of energy densities. And so if you just work out what rho B over rho gamma are, for example, in the two sectors, they end up scaling with exactly the same quantities here, where we've used the fact that the etas are going to be proportional to the reheat temperature, which is itself proportional to the VEV. And so we've gotten most of what we need. We got the VEVs, the temperature being proportional to the VEV of the Higgs in each sector makes it such that the recombination happens at the same time, and that the ratios of baryons to photons in both sectors is the same in terms of energy density. Now, what's interesting, though, is that in the plots that you see from that paper that I was telling you about earlier with Knox and friends, they did this 2-parameter scan, and they allowed the fraction of atomic dark matter to float, meaning that they were varying just how much of the present-day dark matter energy density should be in the form of these primed hydrogen atoms. And they floated that and ended up with some number that was a few percent. In our framework, though, this is a calculable quantity. This is something that, having just told you the story from the previous slides, is a consequence of the relationships between the VEVs and the two sectors. And it just works out to be exactly the number that you would want, or at least something squarely within those ellipsoids for the kind of temperature ratio that they tell us provides a good fit. So this is just an interesting coincidence that by starting off with our premise, we get something that's more predictive than what Knox and all started with, having also resolved those fine-tuning questions, or at least having tamed them to an extent that's not a sextuple coincidence. Now we're going to get back to this question of thermalization. So we need to make sure that whatever operators we write down correspond to interactions that for the reheat temperatures that we're dealing with always give rise to sub-Hubble rates. So what we're asking here is take the hidden sector and the standard model sector and ask, do you produce phi quanta in a Hubble time? And impose some requirement on the suppression scale to ensure that that doesn't happen. And you can do that with some fairly modest choices of parameters, depending on exactly what the dimensionality of the operator is.
What is the massive file?
In this case, it wouldn't matter exactly what the massive phi is, because it was just the energy density and its condensate at that time. I think that this statement would be compatible with any mass as long as it's smaller than the reheat temperature, because we're just asking, what does it take to make a relativistic phi given a reheat temperature in the standard model side?
I guess I'm still worried about other interactions than the ones that we have there, like mediating proton decay or.
Well, okay, I'll write down a concrete one on the next slide. So the choice of the operator will come with its own set of constraints. That's certainly true. So here we're just talking about avoiding thermalization. That's one of the requirements that we would like. We would like to reheat below the electroweak scale because we would like for everything to always scale with the VEV. And if we're reheating above the electroweak scale, that's going to be violated. And so that imposes some requirement on the lifetime of phi and the reheat temperature. So we're gonna be okay with a fairly low reheat temperature. Nothing in principle is gonna spoil us from doing that. So we're gonna want something that can put us below about 100 GeV. And so what we would like though is that for the scalar to be to carry a B minus L number, but for the total operator to be B minus L neutral, because this is going to be responsible for transferring B minus L number into the standard model. So one example for this would be that we add, say, a Dirac fermion and its Dirac partner psi and psi conjugate, such that we write down an operator like this. So we have LH squared. This carries a net lepton number. And we get a net baryon number from adding chi and chi multiplied linearly here. That assigns a certain charge of 2 B minus L units to phi. And then we allow the fermion, once you've produced it, because so phi will decay into the final state particles here, and then chi will decay through the baryon portal into UDD. And that'll transfer the asymmetry in this two-step process. So this would be something that would avoid baryon decay, depending on exactly what flavor structure you have down here. But this would be something where you have to make sure that the suppression scale here would be acceptable. If you're coupling to the first generation, you're going to have a much more stringent requirement on that. But in principle, this combination of things will give a concrete realization to this.
Couple also for prime
Chi?
yeah. Oh,
There will be a chi and there will be a chi prime. Yeah, sorry. So we would mirror everything that's happening here. Yeah. So the summary of all of this is that what's nice about this framework is that alone among all of the super bad, like zinc metal Olympic winners for the Hubble tension, this is an example of something which gives rise to an acceptable fit to CMB perturbations. And so it's worth thinking about ways to realize this that don't make us feel that there are 800,000 coincidences. The scenario that was originally proposed to do this had a number of deficiencies, including the helium problem, which we don't resolve. But it had some model building challenges on top of that, which our scenario is at least in principle able to get around. But it does leave open the question of how to have a successful BBN story in a framework like this. So that's all I got to say, but we're going to give ourselves a report card. So we have some way of getting the asymmetry with the right density ratios and the order of timescales, and the various coincidences work out the way that Knox and friends tell us that it ought to work. We get a fraction of atomic dark matter that can do interesting things in the late universe, but we still suffer the helium problem, so we don't have anything new to say about that. But if someone could figure out a way to solve the helium issue and to tell BBN in an honest kind of way in a model like this, that would by far be the best model for the Hubble tension, but we didn't get there. So that's, now I'm out of time. So thank you.
May I ask you, connection with this, SM prime? There is another tension, and it is tension about Newton lifetime. And this particular, kind of possible explanation was suggested by Zurab-Birijani, and it's kind of about this mixing with mirror neutrons. So it's like your SM prime, but I mean particularly refers in this case to existence of mirror neutrons. And there is this leakage, so there is a mixing of our neutron with this kind of mirror neutron. But I wonder that if in this limited sense, so for example, you have this, let's say that you would accept this kind of mixing of our neutron with this mirror neutron, would it influence to your consideration or not?
So I apologize because I don't think I heard your question very clearly because we're having some technical.
I can relate.
Oh, please
because
do.
I know what Arkady asked.
Okay, sounds great.
So
What is the question?
You're asking about a model where, like this neutron lifetime story discrepant, right? So,
Yes.
so there is our mutual friend Zurab-Birijani who wants N to oscillate to N prime in the trap. And so Arkady is asking whether you can have, if you can add the N prime oscillations and do the neutron lifetime.
I mean, I think that would be difficult in this framework. I mean, there are states that have the kinds of properties that you'd like to have, but we don't want them to be interacting to an extent that I think would be necessary for this, because my understanding is that, like, when people have played games to try to connect this to, say, dark matter, that lives sort of in between the proton and the neutron, they've needed couplings that are big enough that I would expect that whatever operator allows for that to happen would correspond to the two sectors being in thermal equilibrium at early times.
Not necessarily, because I mean, like, it depends how degenerate you are, right? So if not you are, but
I'm very degenerate.
So if they're very degenerate, right? So the very small mixing parameter of the energy units may lead to appreciable mixing angle, right?
So it's a special case where you can have a very close masses, and then you have this mixing Newton and mirror Newton would be enhanced in certain sense, right? So in this sense, yeah, it would be different than the model under consideration. I understand, but I wonder whether it could be relevant to Hubble tension at all.
It could be, but it's not entirely clear. One could make it work, for both anomalies. Right?
Yeah, so we didn't think a lot about this. I mean, if your intuition is that you could do this with phase space suppression and that you didn't need, or that this wouldn't somehow thermalize the sectors, then that would be great.
You can play with parameters as small as 10 to the minus 17 electron volts and make this work, right? Roughly, right? That's if you have exact energy degeneracy, right? And the early universe is still your temperatures are not exactly the same, so the temperature shifts will be significant. So you will 10 minus 17 electron volts will not pose the problems for thermalization. And so on. Yeah.
No. So it's interesting. Maybe there's a connection there, but that's not something that we thought a lot about. Yeah.
So I have a question about lambda QCD. So you said that in two sectors, the lambda QCD is more or less the same.
It's very similar, yeah.
But does it actually depend on the Higgs VEV to the core masses?
It depends a little bit, but it's log sensitive.
But because this pressure appears in the exponent, right?
The two lambda QCDs, so they're like two steps of removal from this. So you're right that it's in an exponential, but the timing is set by when that exponential argument sort of becomes of order 1. And it's kind of a smooth process. It's not like you're falling exactly off a cliff. And then there are two other things. So it's actually quite insensitive to the proton mass because it's the reduced mass of the electron and the proton. So it's almost exactly the electron mass, and then it's log sensitive. So I think it's okay.
Can you go to the slide before the summary slide?
Yes.
Before the summary slide.
Okay.
So yeah, I guess I'm still asking what kind of mass do you imagine for phi, and when does it decay?
Well, so as long as phi is not reconstituted through thermal interactions, its mass doesn't really matter all that much. What you really care about is that when you start off with this Affleck-Dine condensate, that the operator that you write down to deplete the energy density from that can be efficient. As long as the lifetime is good enough that when you've reheated the universe, your temperature is good enough for BBN, then it doesn't really matter. So it's compatible with a wide range of things. So for example, I mean, you wouldn't want it to be, actually, there aren't really very strong requirements on phi. It's just, you have some energy density, you have a lifetime for this thing. So the biggest constraints really do just come from the lifetime, because ultimately the geometric mean of the lifetime and the Planck scale are going to set what the reheat temperature are. So you can't make it so small that you wouldn't get an MEV temperature, but that's the only game. And so there's a sort of optimization game between the mass of the particle, which sets that lifetime, and the denominators of these different scales. So it would be interesting to see exactly how one would map out that parameter space. But I mean, as you've seen, this scenario has a number of additional, maybe more serious challenges having to do with helium, where like at that point, we would like to just be able to show that as a proof of principle, all of these other challenges of this new framework of resolving the Hubble tension can be addressed. The big one still remains. And if someone can get around that big one, then I might be motivated to think a little bit more seriously about how to constrain the mass. But here it's just a sort of proof of principle that if you throw some numbers at this, you can get out a sensible looking universe just at the sort of tilde level from that.
Your notation's a little screwed up there.
Oh, is that right?
It's the middle line. That's not O. Your O is L squared chi squared, or L squared chi R. Because the rest of it you got.
That's right. Yeah, you're right. Thanks for catching that. A copy paste is not always our friend. Yeah.
Any more questions?
So you just lowered the dimension.
Yeah.
Any more questions? Then let's thank the speaker again.
Okay, so maybe you should stay further away from your mic, so we wouldn't overdose the speaker here. Can you hear us? That's the right approach.
He's strategically
Yeah,
decoupled.
That's the right approach to solve my